Okay. So it has been a while. So from the last class, right? Last offline class, actually. So from now on, we will learn about the real-time object detection pipeline. So far we learned about the two-stage object detection pipeline, which is the RCNN stream algorithms, right? So first we learned about RCNN, and then we learned about the fast RCNN and the faster RCNN, okay? So the algorithms are getting faster, and at the same time, their performance becomes better, okay? And then we learned about the DETR algorithms, right? So using the transformer architecture, we developed the object detection pipeline. And after that, we learned about series of works that improves the naive DTR algorithms, right? Such as deformable DTR and the conditional DTR and the DINO, and also what to say. Anyways, we learned about such stream of the algorithm, right? But one thing is that improved algorithm, I lectured it using the online platform, right? So you have to watch that videos, okay? And today we will learn about the real-time object detection pipeline. So maybe some of you are already familiar with the YOLO algorithm. So we will first learn about the YOLO algorithm. And then also recently there appears some real-time pipeline based on the transformer. So after that, we will learn about that algorithm. So actually that algorithm name is real-time DTR. So we will also learn about that, okay? But before proceeding today's lecture, we have to say about this, the final project, okay? So after midterm, our main focus is performing the final term project, okay? So we will operate the leaderboard on the website, and we will also share you with the data set we collected, okay? So our lab members collect this kind of multi-human data set, and we labeled by ourselves the bounding boxes. So there's no annotations available, but it would not be too much difficult to achieve the detection anyways. So our aim is only achieving the human detection. So not detecting other objects, but detecting only humans. So human bounding box detection is the final term project task, okay? And another requirement is you have to develop some real-time pipeline, object detection pipeline, okay? So at least we have to secure 20 FPS for this project. I think that is also helpful for yourself because training such real-time pipeline is also faster than other heavy framework. Okay, so we are aiming to secure some real-time human box detection algorithm. Okay, and we will soon notice about the group making. So maybe 4 to 5 members would be one team, okay? And you have to perform the final project together, okay? And you may also have to secure the GPUs, good GPUs, okay? At least one GPUs per team, okay? And this is the rough schedules for the final project, okay? So 11th of November, there would be midterm presentation, mid presentation for your, not 11th of November, but this week, 13th and 15th of November, during the classes, you have to present your work. But I mean, there are, I think, more than around 10 groups. There would be around 10 groups. So we may have to divide the presentation into two, right? So the group who present first may feel it is unfair to present first, right? So you have to submit all the materials by this date, okay? This is Saturday, okay? Previous week, by the previous week, Saturday, you have to video record your presentation, maybe 10 minutes. You have to record 10-minute presentation regarding your planned algorithm and also your planned data usage and so on. Your plan in the mid presentation, you need to share the plans for performing the final term project. Okay, so plans for data usage and plans for algorithms development, right? So such plans need to be shared by videotaping your presentation by this date, and we will watch it together in next two classes, and we will also proceed the Q&A session, okay? That's the mid presentation. And after 2 weeks, you have to also submit another video having 10-minute content again, by December 1st, okay? And next week's classes are operated to see the watching the video together and having the Q&A session again, okay? This is the two presentations you have to do, right? And final presentation, you have to have more concrete result, okay? In the mid okay? But the final submission date would be here, so 20th of December, right? So there's another 2 weeks gap here, right? So you have to improve your algorithms, and anyways, you have to get the final result of your project and submit all the code and report by this date, okay? That's the final project, okay? And actually, we will operate the leaderboard for this project. And also, we will give you some money as the prize, right? So there, I'm expecting that there would be around 10 groups. And for first, second, and third groups, we will give you some money. But this will be evaluated based on your rankings in the leaderboard, okay? But we will score your project not merely by the ranking, okay? We will score your project based on algorithmic novelty and report and so on. But your performance recorded in the leaderboard will be, to say, rewarded based on this price, okay? So for the score, if you care for only scores and letter degree of this class, then you don't have to much care about the rankings in the leaderboard, okay? You can only concentrate on developing some novel ideas, okay? Any questions? So because there could be a lot of state-of-the-art algorithm, already their code is provided. So one can easily get their code and get the result using that code, right? And upload it in our leaderboard. So sometimes getting first prize is too easy, right? But anyways, that's we are thinking that that is also good effort. So we will compensate it for the money, right? But to get a good score in this class, you have to develop your own idea and your own novelty, okay? How much is small? It is small, it is okay, but it have to be novel, right? It have to contain your own effort. So for example, we will count your effort for collecting data set, okay? Right? Anyways, you try something for improving the performance. So we will count it for the overall score, right? Okay. Anyways, this is the evaluation. So there are two schemes for evaluating for the evaluation. So for the final project score, we will mainly focus on the novelty of your idea. But for the prize, we will focus on the rankings in the leaderboard. The performance itself, we will see. And actually, in previous lectures, we also do similar project, similar competition, and we summarize that and submit it to some domestic conference. So this time we will also do that upon your approval, right? So when making the groups, we will also investigate this. So I mean, you have to check agree or disagree on these things. Okay, so if at least I mean, if one of your group is any member of your group disagree to publish your idea, then we will not include your ideas. Okay, in this paper submission. Okay. But all of your groups agree, then we will include your ideas in this paper submission. Okay, maybe the submission date would be end of December, and we are aiming to submit these ideas in IPIU next year, and that will happen in end of January and end in early February in Jeju Island. Anyway, we will submit it in this conference at the end of this year. And our TA, one of our TA would become the first author, but the next co-author, the order would be determined by your ranking in the leaderboard. Okay. Anyway, I will summarize all of this announcement in the document, the final term project document, and we'll announce it soon. Maybe today or tomorrow, we will announce it, okay? So any questions regarding the final term project? No? So, okay, anyway, if there arise any questions after this, please let me know. Okay. Using some bold or others. Okay. So that is the notice for the final term project, and we will resume our lecture. So I said we will learn about the real-time object detection pipeline. Okay. So far we learned about the two-stage method, right? The first was RCNN, the other was the fast RCNN, and also we learned about the faster RCNN. Okay. The time gradually getting faster and the accuracy gradually become robust. Okay. And also we learned about the DTR-based method. Okay. But they are not real time. Okay, in their speed. Okay. But this kind of approach, the YOLO, their name, by its name, you can imagine how fast it is. So in two-stage method, you may see the images twice, right? For for detecting the object box, you have to see the images once. And after that, for each bounding box, you have to classify their corresponding labels. So in two-stage method, it is likely that you see the images, input images twice, okay? But in YOLO, they do the localization and also the classification at the same time. So it's like you look the images once, okay? So this is the image, this is the input image. And you do two things. This is one thing and this is the other thing. So first, you have to divide it into grid. You will divide the whole image into grid, okay? And normally, in the default setting of YOLO, you will divide it into 7x7 grids, okay? There are 49 grids in the whole image. And then for each image, for each grid, you will estimate two bounding boxes in default, in YOLO with the default setting, you will estimate two bounding boxes for each grid, but you can change it actually. And for each grid, you estimate the class probability, okay? Then you will have some result looks like this with some class probability, but for redundant boxes, you will remove them using some algorithm, which will be explained later. And then you can get this kind of refined result, okay? So this is the conceptual figure for YOLO algorithm. But that could be, that actual pipeline could be drawn like this. So this is the input image, and this is the output for YOLO pipeline. So you can see their final output, their dimension is 7x7x30, okay? Here, the 7x7 means the grid, okay? And 30 is constituted with this vector, okay? So among 30-dimensional vector, the first two are indicating the number of, this is estimating the bounding box information, okay? So I already said you that in YOLO, you will estimate two bounding boxes for each grid, right? So one bounding box information is constituted with this 5-dimensional vector, okay? So because we are estimating two boxes, 10-dimensional vectors are reserved for the box information. And here, in this application, you are dealing with the classification with 20 classes. So that 20-dimensional vectors are reserved for the class probability, okay? So estimating this vector, this 30-dimensional vector is estimating these two information, is equivalent to estimating these two information, right? So these two 5-dimensional vectors are representing the bounding boxes, two bounding boxes, okay? And this 20-dimensional vector is representing the class probability for each grid, okay? This color encodings are encoding the class name, okay? If it is pink, it is denoting the bicycle, and it is the orange color denotes the car, and the green color denotes the dog, and so on, right? For each grid, we estimate class probability as well as the bounding box information, okay? That's actually this 30-dimensional vector, okay? Everyone follows me? Okay. And these 30-dimensional vector are estimated for 7 by 7 grids, right? So actually, estimating these 7 by 30-dimensional arrays from whole image can be represented like this, right? So this is the YOLO algorithm. Okay. So, and this slide is showing that why 5-dimensional vector is required for representing one bounding box. So previously I said you 5-dimensional vector is required for one box estimation, right? So why 5 dimensions are required is because we have to infer this 5-dimensional information, okay? So the first and second, they are representing the center positions that x comma y, center positions of the bounding box. That's first and second dimensional information. And third and fourth, they are denoting width and height of the box, okay? We need at least these four information to represent one bounding box, okay? And the other information we have to infer is the confidence value for the bounding box, okay? So in YOLO, you have to also estimate this confidence value. Please assume that, let's say there are one ground truth object in this image. So this is the ground truth bounding box location. Let's assume like that. Then ideally, let's say there are 5, 5, 5 grid like this. Then in this grid, you need to estimate, you need not to estimate any bounding box, right? So because ground truth is only here, the boxes estimated from these grids will be correspond to this object, right? But the bounding box, which will be estimated from these grids, cannot estimate this bounding box, but estimate some bounding box nearby their grid. So because there are no object, these bounding boxes have to be suppressed, ideally, right? But in YOLO, every grid estimates same number of bounding boxes. For example, in previous example, we have to estimate 2 bounding box from every grid, okay? So we need this kind of confidence value to be estimated. So for these grids, because there is no ground truth, we suppress this confidence value towards 0, indicating that there is no object, okay? And for these grids, they estimate 2 bounding boxes, and these confidence values become close to 1, okay? But not exactly 1, but they actually estimate 1 multiplied by I or U, So IOU, I will explain it in later, but now I will explain it slightly. So IOU is the intersection over union. Okay. So this is the measure for measuring how two bounding boxes are intersected. So I will show this figure first. So this is the IOU. This is the intersection over union. This is, you can think this is the intersection. Overlap is equivalent to intersection. Intersection over union. Okay. So in here, union, let's say this is the bounding box you estimate. Let's say this is the estimated bounding box, and this is, let's say, ground truth bounding box. Okay. If estimation is accurate, it have to be exactly same as the ground truth. So this is the ideal case. And their union is just the ground truth area, right? And their intersection is also ground truth area. So in ideal case, the intersection of a union becomes one, right? And if they don't meet, then their area is, this is A, let's say this is area is A and B, and their intersection becomes 0, so their IOU becomes 0, right? So this IOU is measuring how two bounding boxes are intersected, okay? If they exactly same, their value becomes 1. If they don't meet, then it becomes 0, right? And because between 0 and 1, their values are including the ratio of intersections over their union area. Okay, this is including how two bounding boxes are intersected. Anyways, so for objects, for the grid which have ground truth object within it, then it estimate 1 multiplied intersection over union value. Okay, they will estimate some confidence value for that bounding box. Okay, that's a 5-dimensional value for reserved for the bounding box estimation. Okay, so for each grid, you will estimate bounding boxes, and at the same time, you will estimate their class probability. Okay, there are ideally, because there are 49 grids, there are, and for each grid, we estimate 2 bounding boxes. There are 98 boxes estimated. Okay. So if we visualize it, it looks like this. So after estimating this dimensional array from the input image, the initial result looks like this. And after doing some post-processing, whose name is non-maximal suppression, NMS, the result becomes like this. And this is the final result of the YOLO. Okay. So from the YOLO architecture, you will obtain this dimensional array. Okay. If you correctly train the YOLO algorithm, you can get this type of output. Okay. And then you will apply NMS operation, which will be explained later, to refine the result. Okay. We will explain it later. And this is the loss function. you have to use to train the YOLO algorithm. Okay. So it looks complex, but if you see one by one, it's very simple. So the first line and second line, what they are doing is training the bounding box location and their width and height. Okay, so this is location, center location of the bounding box. This y and x, and head is the ground truth. Okay, so we are basically closing the center location of the box to their ground truth. Okay, but we do this for grid and box, each grid box, which have this flag as one. Okay. So this, you have to note these four flags. This will become one full grid, and each grid box who have the object ground truth and also which is close to the ground truth. Okay, so I mean I is index for grid. So this S is now 7. Okay, so this I is index for grid, and J is index for two bounding box, but there could be more bounding box. We are, so in here, we are assuming that we will estimate two bounding box, but this B could be larger than 2, right? And also, this is 2 now. This S is 7 by, denoting the 7 by 7 grid, the number of grid, but this could be also variable, right? So we write it as S and B here, okay? So basically for each grid and for each bounding box, we close its center position close to the object ground, their ground truth. When the ground truth exists, right? So this flag exists when the ground truth exists for that grid. And also among two boxes, we select the one which is close to the ground truth, and then apply these laws to that. Okay. And it's same for this width and height. Okay. So for all the grid and for all the candidate bounding box, we close their width and height to the ground truth value. Okay. When there is ground truth object box, and when the box, candidated box, is close to the ground truth. Okay. And these two, before explaining this, I will explain this first. And we have to also estimate the class probability for each grid. Okay. And this PI is denoting the 20-dimensional vector. Okay, this was there was two 5-dimensional vector for estimating box, and there was one 20-dimensional vector for estimating the class probability. Okay, so this is denoting our 20-dimensional vector. So this is our output, and there should be the ground truth. Okay, there should be some ground truth class probability for each grid. So we anyway apply the MSE laws on that to make this estimate the ground truth probability, okay? And we do that when object exists for that grid, okay? If there is no object ground truth within that grid, we do not apply this loss. This loss is applied only when ground truth object box is there, okay? And these two are applied for the confidence values, okay? So, I mean, here, our output looks like this, right? And this 20-dimensional vector is their losses applied with this term. And for these two bounding box information, their x, y, and reduced height, the 4-dimensional values are applied with these two terms, okay? The remaining term is the confidence values, okay? And that's obtained using these two terms, okay? And we divide the case to two cases. So the first case is when the grid has the object ground truth, and the other case is when the grid does not have any object ground truth. So this becomes one when the object ground truth in the grid. So if it exists, we make our ground truth by multiplying, by making it close to 1. And when there's no object, then we set this as 0, okay? So this is the confidence training, okay? So ideally, this CI becomes 1 when object exists, and this becomes 0 when object is not exist in the grid, okay? So this is the loss term to train this 7 by 7 by 30 dimensional array, okay? So this is quite simple architecture, right? From the whole image, you will estimate this dimensional array, and their loss functions are applied in this manner. Depending on the location of the ground truth, you have to make your corresponding ground truth first, and then apply this kind of loss function. Any questions? Okay. So this is the code for generating the ground truth. Okay. So it is also not very hard, but thing is, your network looks like this, and the ground truth we have is like this. So this is the image, and this is some ground truth object we have. Okay. Maybe if you annotate each image, you will annotate it like this. Their class and width height, center X and center Y. This information is the information you will annotate, right? But you have to make this dimensional array from the ground truth to train this network, okay? So you cannot directly use your ground truth to train your YOLO network, but instead you have to process this ground truth information to make it fit to this dimensional array, okay? And that code actually lies here, okay? So your ground truth now becomes this. You have to make this dimensional array by yourself, and you have to fill that ground truth properly using the ground truth box information you have. Okay. And these boxes are some ground truth box information you have. Okay. From here, you have to make the width and height and the center X and center Y. Okay. Okay. Here, they are assuming that the box information is having 4 information, but 4 informations are denoting this, right? So for CX and CY, you have to add them and we'll divide it by 2, okay, to find center positions from this x1, y1 and y2, x2, y2. And also for width and height, you may have to subtract x2 by x1 and y2 by y1. Okay, so that's the way to recover the width and height and center x and center y. And also for the candidate boxes, you have to also fill this kind of box information. So here, this is the 5-dimensional information, and this is the 20-dimensional information. And you have to fill the CX and CY and width and height for first 4-dimensional vector of this array. So that is actually happening in here. And also the confidence values are set as 1. These confidence values are set as 1 when the objects are inside the bounding box. Okay. And also for this part, that is initialized here. So this is label information, and this is the 10 offset. Okay, so you know the labels in ground truth, and it is added with the starting point, the 9 position, and one of dimension is becoming 1, and others are becoming 0. Okay, in ground truth, it is 1 hot encoded, so only one class is having just 1, and others have 0 probability. Okay, this is the ground truth. So anyway, this code is required to make this the ground truth of this dimensional array from the ground truth object ground truth. Okay. So are you guys following me here? 다 이해되나요? 근데 뭐 그렇게 어려운 얘기는 아닌데 영어로 하다 보니까 이게 전달이 안 될 수도 있는데, 그러니까 여기서 이거를 그냥 이렇게 생긴 디멘전을 추론을 하는 건데, 우리가 가지고 있는 거는 어떤 이 영상에서 바운딩 박스 인포메이션이나 레이블 인포메이션밖에 없잖아요. 그래서 그거를 이 7x7x 30으로 바꾸는 과정을 해야 되고, 그래서 이제 각각마다 똑같게 해주도록 하면 되는데, 그 바꾸는 코드가 이제 이게 디멘전 그 이미지에 있는 바운딩 박스 좌표로부터 이런 7x7x 30 디멘전의 어레이, 그라운드 트루스 어레이를 만드는 거를 지금 하는 코드가 이거라는 겁니다. 그리고 이거 각각을 어쨌든 뭐 위드 사이트는 이걸로 가깝게 해주고, 뭐 그 다음에 여기는 프로버빌티 가깝게 해주고, 여기는 오브젝트가 그 셀에 있으면 1이고 없으면 0이고 이렇게 가깝게 해준다는 얘기입니다. And this is the code for applying the laws in your law. So this is quite long. Okay, but you can see here the total laws. The laws is same as I presented previously. So This is the loss for XY center, and this is the loss for width and height. This is the loss for confidence for objectness, and this is the loss for known object, and this is the loss for class probability. Okay, this is the final, but you will see in here there's some selection process for all the predicted bounding box information. You have to select the boxes with object or boxes with non-object. So you will threshold it by the estimated confidence value. If it is larger than 0, the network is saying that there is some probability that there would be object. So if the estimated confidence value is larger than 0, then we set this mask for that bounding box as 1. And the network estimate its confidence as 0. We set the bounding box as the non-object bounding box. Okay. And anyway, in the later code, we select the bounding boxes which have objects only and apply these four losses, which is the width closing the center location to its ground truth, and width to its ground truth, and the confidence value to 1, and closing the class probability to the ground truth. And for the bounding box, which do not have any object inside, that is also calculated here. So for that bounding box, we close the 0 confidence to its output confidence. Okay. Anyway, this loss function is also implementing the same thing denoted here. Okay. Anyway. So, I mean, if you read the paper, YOLO paper, you can only see this type of figure and some of architectures like this. And the thing you have to convert your ground, you have to make your own ground truth. This dimensional ground truth was omitted in the paper. So I'm wanting you to think about that, seeing this code and other details. Okay. Okay. So, and also, this is the IOU I already explained to you. And this is actually the code for calculating the IOU. Okay. So, but this code is made for multiple bounding boxes. So box 1, that can have m number of boxes, and this second argument, it also has n number of bounding boxes. And here IOU, it output their paired IOUs. Okay. Actually, there are n by m number of IOUs returned. Okay. And actually, what they do is here, they calculate the intersection regions. They actually detect this point and this point, okay? And actually calculate this region's area, and also calculate the original region's area, for example, A and B. And let's say this is intersection I. Then you can calculate the intersection over how to say union like this. So this is A plus B minus intersection area. This is the union, and this is the intersection area. So this is actually IOU. Okay. Anyway, this is the code for that. Please refer it. Okay. So union is calculated by area 1 plus area 2 minus intersection. And intersection over union is IOU. Okay. So this is simple code actually. And also I have to explain this part, the NMS. So when we get the 7 by 7 by 30 dimensional array from the YOLO architecture, their output looks like this, having many redundant frames, okay? And we have to refine it like this. So when doing that, what we do is we remove among two bounding boxes, we remove one having better confidence. Okay. If there are among two bounding box having large IOU, having large IOU means two bounding boxes they are having large amount of intersections. Okay, so we will remove one, remove one, remain one, remove one who have less confidence value. Okay, we will remain one having higher confidence value. Okay, so if two bounding boxes are having much redundancy, then we will remove one which have less confidence value. Okay, that algorithm is actually the non-maximal suppression. Okay, and you can see the algorithm here, right? So basically, we sort the scores, the confidence values, the bounding boxes having, and remove one which have less confidence. Okay, that's the non-maximal suppression. So this is the YOLO algorithm, actually. So what YOLO do is this. So they actually train this architecture by making proper ground truth arrays from the original ground truth, and then train this. And for unseen input image, they estimate this 7 by 7 by 30 dimensional bounding box information. And then they can get this type of redundant bounding boxes predicted, and then they refine it using NMS. Okay. So the algorithm works fast. Okay. So everyone understand how YOLO works? Okay. Any questions?
Why aren't they using MSC for the class part?
And MSE instead of the cross entropy, why they? I don't know either. So maybe ask authors. Yeah, but the ground truth information they represent is because of, I don't know the exact reason, but because of that, anyway, the representation itself changed as the one-hot encoding, right? Rather than the binary index, right? Maybe they want to make things simpler, maybe, I'm not sure, yeah. Maybe you can apply the cross entropy laws for the class part, maybe it will work, I think. Yeah, you mean this part, right? Maybe you can change it as the cross entropy laws in that case. Other questions? Everything is clear? So because of the different architectures they have, the YOLO algorithm say their error patterns are slightly different from the two-stage algorithms, like the fast RCNN algorithm. So maybe fast RCNN, they involve more errors in the background regions, but YOLO exhibit less error in background, but the localization, the box estimation is more accurate in the fast RCNN. Okay, so, but this is the error pattern for YOLO version 1. But the thing is, YOLO version 2, this graph is quite interesting. So we learned about the RCNN, fast RCNN, and faster RCNN here, right? And the x-axis, it is denoting the speed, frame per second. This is measuring the speed. So per 1 second, how many frames are processed by the algorithm? Okay. So if you can process more frames per second, then it means that algorithm is faster. Okay. So YOLO, it can process more than 30 frames per second. So if you this dotted line, this is the criteria for real timeness. So normally we say if the algorithm operates faster than 20 or 30 frames FPS, then we call it as the real-time algorithm. Okay, YOLO, they are a real-time algorithm. Okay, and the y-axis, they are denoting the accuracy. Okay, so RCNN, fast RCNN, faster RCNN, they become faster. Okay, and at the same time, their accuracy becoming better. Okay, so original YOLO located here, right? YOLO originally, they are faster than RCNN stream work, but their performance was worse than that. But YOLO version 2, it is faster than RCNN and also faster than YOLO, but it is even better than RCNN stream algorithms. Okay, so after this YOLO version 2, many companies are using this YOLO algorithm instead of two-stream algorithms. Okay. Okay. And maybe we will deal with this RTDTR maybe in the next class. So this is quite recent technical report. It is not published yet, but I think their performance is very good, and at the same time, they are having the real-time speed. Also, they are based on the transformer architecture. So the title of this technical report is quite appealing. So DTRs now beat YOLOs on real-time detection tasks. Okay, so we will see this next time. Okay, and also next time we will review the YOLO version 2 and also the YOLO version 3. Okay, so how YOLOs become enriched, I will review that. Okay, thank you for attending this class. Thank you. Let's finish here. Okay, if you have questions, please let me know after the class.